Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at a few examples of how do we use differential continuity equation in engineering problems. We have derived the equation before, so now is the time to see the problem and relate how can we use those equations to solve that particular problem. So first of all, we are going to be looking at example number 1. In this example, you have a pipe that is carrying water, and now let's assume that inside this pipe is a steady and uniform flow. Okay, and I have 3 measurement points inside this pipe, which I'm going to call point A, point B, and point C. And what I measure here at these points are the velocity. So at point A, I found that my velocity here is 83 meter per second. At point B, my velocity is 86 meter per second. And at point C, my velocity is 88 meter per second. This means that as the flow moves along the pipe, the velocity is actually increasing. Now this can happen even the flow is a steady flow, because steady means the velocity remains the same at that particular location. For example, at point A, when you look at it now, it is 83 meter per second. And then you look away and you look at it again, it is still 83 meter per second at point A. So that is the definition of steady flow. Now back to our example, the distance between point A and point B is 10 centimeter. And likewise, the distance between point B and point C is also 10 centimeter. And it is given that at point B, the temperature is 10 degrees Celsius and the pressure at point B is 345 kilopascal. Now, the question is asking what is the del rho over del x at point B. So this equation implies that the density of the flow is actually changing as it moves across point B. So first of all, what I'm going to do is to simply write the equation that we have derived before. And that equation is this one. Okay, so what I will do is that I'm going to copy this equation, or simply I'm just going to rewrite it again so that you can see. Del rho over del t plus u del rho over del x plus v del rho over del y plus w del rho over del z plus rho del u over del x plus del v over del y plus del w over del z, and this is equal to 0. Now what we need to do next is to find a few parameters that we can actually cancel out to ease our calculation. Now first of all, it says here that our flow is steady. Now steady means that the flow does not change with time. So whatever change that is associated with time, we can cancel it out. I think we can clearly see that del rho over del t will become 0. And our second assumption, perhaps the most important assumption, is that the flow is uniform, meaning that there is no change in flow across y and z direction. We know that the flow is changing in x direction because you can see that the velocity is changing as it moves along x direction. But in terms of y and z, the flow does not change at all because we assume that the flow is uniform. Okay, so because of that, any changes associated with something that is not x, we can cancel it out. So we can cancel this term and cancel this term, and we can also cancel del v over del y plus del w over del z. So what remains now is everything that is related with changes in x direction. Okay, so what we have here is u del rho over del x plus rho del u over del x, and this is equal to 0. And do you remember what we need to look for? We need to look for del rho over del x. So we need to look for this parameter at point B. And I think from this equation, you already know a few things. First of all, you know what is u at point B, right? At point B, the velocity is 86 meters per second. So that is done for you. And do you know what is rho? What is the density at point B? I believe we do not have that information. But thankfully, we have these two parameters. So what we need to do now is to use the ideal gas equation to obtain what is the density at point B. So from ideal gas equation, we know that P equal to rho times R times T. So rho equal to P over RT, and our pressure is 345,000 divided by R. R is 287 times the temperature. Temperature is 10 degrees Celsius, and you need to convert it to Kelvin. So plus 273, and this becomes, so this is 10 plus 273 times 287, 345,000. Divide by answer. So that becomes 4.25. And the unit is kilogram per meter cube. So now what you have from this equation, you already have the velocity, and now you also have the density. The only thing remaining is that you need the del u over del x. That is the change of u in x direction, the change of velocity in x direction. If we go back to our diagram now, because we have the similar length here, which is 10 centimeter. So point A and point B is 10 centimeter apart, and point B and point C is also 10 centimeter apart. So to obtain the change in velocity at point B, you can actually use point A and point C to determine it. Okay, del u over del x can be approximated by the change in velocity over the change in the x direction. So this will be 88 minus 83 divided by 20 centimeter. That will be 0.2 meter. And therefore, this becomes 88 minus 83 is 5. 5 divided 0.2 is 25. And the unit is meter per second over meter. And now, I believe that you have everything that you need in order to find del rho over del x. So if I can write it here, now u is 86. Okay, so 86 times del rho over del x plus rho is 4.25 times del u over del x. This is 25 equal to 0. So your del rho over del x is 4.25 times 25. That will be negative answer divided by 86. So that will be minus 1.24 kilogram per meter cube per meter, or simply 1.24 kilogram per meter to the power of 4. So this is now your final answer. Okay, so if I can recap what we have done here. So basically, we have this equation. Okay, there's no need to derive it again because you have already derived it from the previous video. And if you memorize the equation, you can just write it. And the next step is to eliminate the terms that is not used in this problem. Okay, and the most important assumption is this, which is steady and uniform flow. From that assumption, you can remove a lot of terms inside this equation. And you are left with only this equation, right? And from there, use whatever information that the question gave to find del rho over del x, which is the change of density in x direction. Okay, and once we found that, we determine that our del rho over del x is minus 1.24 kilogram per meter cube per meter, which means that as the flow moves to the right hand side, the density will keep decreasing and decreasing. Okay, I hope that is clear to you. Now, let's move on to example number 2. Okay, so example 2 is where you have a converging pipe that looks something like this. Okay, and in this converging pipe, you have 4 points, which is point A, point B, point C, and point D. And the flow is moving from left to right. And similar with the previous example, we have measured what is the velocity at each of these points. And the velocity is given to you, where at point A, the velocity is 5.76 meter per second. At point B, the velocity is 6.72 meter per second. At point C, the velocity is 7.61 meter per second. And finally, at point D, the velocity is 8.47 meter per second. So in general, you can see that the velocity is actually increasing, which makes sense because the flow area is reducing. And the distance between these points are 10 millimeter apart. So this is 10 mm, 10 mm, and 10 mm. And another important information that's given to you is that the velocity in z direction, which is w, is 0 meter per second. And the question is now asking for two things. The first thing is that, what is the x component of acceleration at point C? Okay, so we denote this as acceleration of x at point C. And then the second one, the question is asking for the velocity in y direction (6 millimeter above point B. Okay, so velocity in y direction, so this is basically v, 6 millimeter above point B, so probably somewhere here, right? And our assumption is first that the flow is incompressible. Secondly, the flow is steady. And finally, that the flow is symmetrical. Meaning that the flow profile above the ABCD point is similar with the flow profile below the ABCD points. Okay, now let's figure out how to solve this problem. So basically, what is acceleration? Acceleration is simply velocity divided by t. The change in velocity divided by the change in time. And we know that in a fluid flow, the velocity can be represented as three components. You have x component, and then you have y component, and then you have z component. And velocity is actually a function of x, y, z, and also function of time. So if I want to find a small change in velocity, this is actually dv. So I must do the partial differential, which is del v over del x times dx plus del v over del y times dy plus del v over del z times dz plus del v over del t times dt. And therefore, if I plug it in here, now let's remove this x first. Okay, so acceleration in general, what you're going to have is acceleration equal to del v over del x dx over dt plus del v over del y dx over, this is dy over dt plus del v over del z dz over dt plus del v over del t dt over dt. And before we move on, let me make it clear to you that these are capital V. Okay, so these are capital V, which means that this is a velocity that contains velocity in x direction plus velocity in y direction plus velocity in z direction. So this is also capital V. These are all capital V. Please do not confuse later on with the small v, which is the velocity in y direction. We'll see afterwards. Okay, so now if you notice, dx over dt is actually u, which is the velocity in x direction. dy over dt is actually v, which is velocity in y direction. dz over dt is actually w, which is velocity in z direction. Now let's write them up. Okay, so this is still del v over del x times u plus del v over del y times v plus del v over del z times w plus del v over del t, and this is definitely equal to 1. Now let me make this clear again. This is still capital V, this is capital V, and this is also capital V. And now when we talk specifically about x component of acceleration, which means that we are looking for acceleration in x direction. So if I write here acceleration in x direction, okay, all the capital V now change to small u, which we consider only in x direction. So if I rewrite this, so this will become u del u over del x plus v del u over del y plus w del u over del z plus del u over del t. So this is your acceleration term in x direction. Okay, so this is the equation that we are going to work with to solve question number 1. Okay, now let's see if we have a few components of this equation that we can cancel out. Okay, first of all, it says here that w is 0. So immediately we know that this term is 0. Next, we also know that the flow is steady. So again, there is no change in time, meaning that del u over del t is also 0. And when we assume that the flow is symmetrical, meaning that at the center line of this pipe, there is no velocity in y direction. There's only velocity in x direction. Okay, so we can say that this is also 0. This means that we are now left with this equation ax equal to u del u over del x, and the question is looking for s component of acceleration at point C. I think we know that at point C, the velocity is 7.61 meter per second. So this is equal to 7.61, and del u over del x again is del u over del x is delta u over delta x. Now let's take a look at point C. Right, so now we can use point B and point D as our reference. So point D is 8.47 minus 6.72. So 8.47 minus 6.72 divided by, I believe this is 10 millimeter times 2, 20 millimeter, which is 0.02. And this is equal to 8.47 minus 6.72 divided by 0.02. This is 87.5 meter per second per meter, meaning that our acceleration is 7.61 times 87.5, which is equal to times 7.61, 665.9 meter per second square. That is the unit of acceleration. So this will be your answer for question A. And now let's take a look at question B, which is the velocity in x direction 6 millimeter above point B. I believe to solve this, we are going to need the continuity equation. Now, because our flow is incompressible, now let's see what is the equation for continuity for incompressible flow. And I believe the equation looks something like this. Very simple. So del dot V equal to 0. Del dot V equal to 0, which means that del U over del X plus del V over del Y plus del W over del Z equal to 0. And we know immediately that del W over del Z is 0 because W is 0 anyway. Okay, and it's given in this assumption. Okay, now we are left with del U over del X equal to minus del V over del Y. And I think we can approximate this with the change in U over the change in X direction is equal to the change of V over the change in Y direction. Okay, so if I move the negative sign here, so we get here delta V over delta Y equal to negative delta U over delta X. And now our point of interest is point B. Okay, so at point B, we can figure out what is delta U over delta X by using point A and point C. Okay, so this is 7.61 minus equal to negative 7.61 minus 5.76. This is divided by 0.02 and this is equal to 7.61 minus 5.76 divided by 0.02, 92.5 meter per second per meter. And let's not forget the negative sign in front. Okay, and now we are looking for velocity in Y direction, which is V 6 millimeter above point B. And I think we agreed before that the velocity in Y direction is 0 at the center line because we said that the flow is symmetrical. Okay, so what happens now is that I'm looking for delta V at delta Y equal to 0.006 because 6 millimeter, right? So this becomes minus 92.5 times 0.006. And this is equal to times 0.006, negative 0.555 meter per second. And because we know that the V at center line is 0, so the velocity 6 millimeter above point B is minus 0.555 meter per second. So that will be your final answer for the second question. Okay, and if you notice, this question number 2 is actually a little bit more complicated than the previous example. But if you look at it very carefully, there's actually nothing strange about these questions. What you only need is this equation. So basically, because you have derived this equation in the previous video, and now you can see how this equation works in solving the engineering problems. I believe now that you can see you need a proper understanding about this differential equation before you can use it in actual engineering problems. You can solve basically almost anything using this continuity equation in differential form. And my advice to you is to do this example 1 and example 2 again and again until you can do it even without looking at your notes. That is all from me for now, and I'll talk to you soon. Bye!